Here we have a problem that we have multiple steps to solve. We're going to be feeding air into a compressor, and so air is entering here. To increase the pressure to 15 bar, and the gas flowing out of the compressor is fed into a tank, and then the compressor shut off when the tank pressure equals 15 bar. And the question is, if the efficiency of a compressor is 80%, how much work does it take to fill the tank? So this is going to require solving for ideal gas, determine the number of moles in the tank, solving for the temperature leaving the compressor, and then solving for the temperature in the tank. So first, let's label the diagram so we know what information we have. So I've labeled the diagram, the starting conditions in the tank, call N1 the number of moles in the tank, beginning. At the end, we're going to end up at 15 bar, temperature T3 that we have to determine, and the number of moles N3. So number of moles that we flow into the compressor, that number N is N3 minus N1. So first, let's use the ideal gas law, then number of moles initially, pressure 1, the volume of the tank over R, and the temperature in the tank. We'll call that T1 since it's the same as the inlet temperature. And then when we're finished, N3, pressure 3 is 15 bar, the volume is the same, R, and temperature 3, we're going to have to solve for it. So we now know the number of moles initially in the tank, and we have a relationship between the number of moles at the end in the tank and the temperature. So now let's look at this compressor. In order to calculate the outlet temperature, first we're going to have to solve the reversible compressor. So if we look at the equation for reversible adiabatic compressor, then let's call the reversible temperature T2R over T1. This is for adiabatic reversible constant heat capacity. So R is in units of joules per mole per Kelvin. And I've used the heat capacity for air that I think is going to be appropriate over this temperature range, since we're going to end up relatively high temperature compared to the feed temperature. We can see 628 Kelvin is the temperature if it were reversible. And so now we can calculate the reversible work and then use the efficiency to get the irreversible work. So the work for the reversible compressor is equal to delta H for reversible, which is the heat capacity times the temperature difference, reversible outlet temperature, inlet temperature. And so this reversible work, well, the irreversible work is going to be larger. Let's just call that the actual work for the process. And that's going to be reversible work divided by the efficiency. The efficiency is 80%. Well, irreversible work is larger. I can go back now and relate that work to the actual delta H through the compressor, which of course is Cp, the temperature for the irreversible, leaving the compressor, minus the inlet temperature, 295 Kelvin. So let me again pause and substitute in these numbers. So I have the temperature now leaving the compressor, entering the tank, and so now I'm going to use the energy balance on the tank, an unsteady state process, and that's going to say the number of moles that are in the tank at the end times the internal energy minus the number of moles we start with, internal energy, where the internal energy is per mole, is equal to the number of moles that we flow in, which is N3 minus N1, times the enthalpy entering the tank, and it's the enthalpy at 711 Kelvin. So I'm going to use U in terms of reference value, since we're interested in differences, and CV for air, T minus T reference. Where I'm going to pick values to make life easy, I'm going to make the reference temperature 295 Kelvin, and at that reference temperature, I'm going to make U reference equal to 0. Well, that means H coming in has to have the same reference. Well, that's UN plus PV entering. Now, UN is CV T2 minus the reference temperature, and PV is our T2, ideal gas law. This H is per mole, therefore volume per mole. So let me go back and substitute into this energy balance. We have N3 times the constant volume heat capacity, temperature 3, the final temperature in the tank, minus our reference temperature. And now U1 because our choice of reference, since we're at 295, this is 0. And then the right side of the equation, N3 minus N1, that's the number of moles that we've added to the tank. And I'm going to substitute in for HN with this. Okay, now I'm going to substitute where CV is going to be CP minus R. So this is 29.8 minus 8.3, 21.5 joules per mole Kelvin. Again, so I made the substitution. N3 and T3 are unknowns, but we have this relationship between N3 and T3. So I'm going to substitute in for T3 in terms of N3. Have equation one unknown. We can solve for N3. So I made the substitution, solve for N3, and therefore T3, which is 4513 over N3, 5.29. So the final temperature in the tank, 853 Kelvin. Well, we want the total work into the tank. So work total is going to be number of moles that we flow through, which is N3 minus N1, times the work per mole, which we calculated at 12,404 joules per mole. So the total work would be the 5.29 minus 1.02 multiplied by the 12,404 joules per mole. So the total work is 52,965 joules, which is 53.0 kilojoules. That's the work required to pressurize the tank to 15 bar.